If you're building a solar power system, setting up an RV, or installing batteries in a camper van, one question always comes up. Should you wire your batteries in series or in parallel? Although both methods connect multiple batteries together, they produce very different results. The battery voltage changes, the available capacity changes, and even the type of equipment you can use depends on how the batteries are connected. Many beginners understand the basic idea but still make wiring mistakes that can reduce battery performance or even damage the battery bank over time. So, in this video, I'll explain how series and parallel battery connections work, using simple real-world examples. Whether you're using lead-acid batteries or lithium batteries, you'll understand when each wiring method makes the most sense and what mistakes you should avoid. I'm Michael, and welcome to Battery Hacker. If you enjoy practical battery and solar content, don't forget to subscribe, give this video a like, and if you have any questions, leave them in the comments below. Now, let's begin with the fundamentals. When batteries are connected in series, the voltage increases, but the battery capacity and amp hours stays exactly the same. For example, if you connect two 12-volt, 200 amp-hour batteries in series, the result is a 24-volt battery bank with a capacity of 200 amp-hours. This configuration is commonly used in larger solar systems, RVs, and camper vans that operate on 24 volts. The biggest advantage is that increasing the system voltage reduces the current required to deliver the same amount of power. Lower current means less heat in the cables, lower power losses, and, in many cases, smaller cable sizes. Now, let's look at a parallel connection. With batteries connected in parallel, the voltage stays the same, but the capacities are added together. So, if you connect two 12-volt, 200 amp-hour batteries in parallel, you'll still have a 12-volt battery bank, but the total capacity increases to 400 amp-hours. That extra capacity allows your battery bank to run your loads for a longer period before it needs to be recharged. This is a popular option for people who want to keep a 12-volt system while increasing runtime or supplying enough current for a larger inverter. There's also a third option called a series parallel connection. This combines both wiring methods to increase both voltage and battery capacity at the same time. For example, with four 12-volt, 200 amp-hour batteries, you can create a 24-volt, 400 amp-hour battery bank by first making two series pairs and then connecting those two pairs in parallel. Before connecting any batteries together, there are a few important rules you should always follow. Every battery in the same battery bank should have the same nominal voltage, the same amp-hour capacity, and the same battery chemistry. For example, you should never connect a lead-acid battery directly with a lithium battery in the same series or parallel bank because they charge and discharge differently. It's also best if the batteries are the same age and in similar condition, especially with lead-acid batteries. Mixing an old battery with a new one usually causes the weaker battery to limit the performance of the entire battery bank. Another important point is state of charge. Before making the connection, all batteries should be charged to approximately the same level. Otherwise, a large balancing current can flow between the batteries as they try to equalize, and that creates unnecessary stress. Finally, if you're wiring batteries in parallel, try to use battery cables that are the same length and the same size. This helps each battery share the load more evenly, improving both performance and battery life. Now that we've covered the basics, let's move on to some practical examples and see how these different battery connections perform in real-world situations. We'll start with a 1000-watt inverter running on a 12-volt system. First, let's use a single 12-volt, 200 amp-hour lead-acid battery. This example applies to AGM and gel batteries because they follow similar discharge recommendations. A commonly recommended continuous discharge rate for lead-acid batteries is around 0.2 C. That means you should only draw about 20% of the battery's rated capacity each hour if you want good long-term performance. The calculation is straightforward. 0.2 multiplied by 200 amp-hours gives a recommended discharge current of 40 amperes. Now, let's compare that with what the inverter actually needs. A 1000-watt inverter running from a 12-volt battery will draw approximately 1,000 watts divided by 12 volts, which is about 83 amperes. That means the inverter is asking for more than twice the battery's recommended continuous discharge current. Will it work? Yes, it probably will. But running a lead-acid battery this way on a regular basis isn't a good idea. The higher current can increase internal heating, reduce efficiency, shorten battery life, and over time lead to a noticeable loss of usable capacity. If the inverter is only used for a short period occasionally, it may not be a major issue. But for frequent or extended use, this setup is far from ideal. Now let's improve the system by adding another identical battery in parallel. With two 12-volt, 200 amp-hour batteries connected in parallel, the voltage remains 12 volts, but the total capacity increases to 400 amp-hours. Now, let's repeat the calculation. 0.2 multiplied by 400 amp-hours equals 80 amperes. The inverter still requires about 83 amperes, so the battery bank is now operating much closer to the recommended discharge rate. In other words, the workload is shared between both batteries, reducing the stress on each one. This setup is much better suited for regular inverter use and should help extend the life of the battery bank. The trade-off, of course, is that you've doubled the number of batteries, which means more weight, more space, and a higher overall system cost. There is another point that's worth mentioning. Even when you stay within the recommended charge and discharge current for lead-acid batteries, the depth of discharge also has a major impact on battery lifespan. In general, the less deeply a lead-acid battery is discharged, the longer it tends to last. For example, if you only use around 20% of the battery's capacity during each cycle, it can often deliver significantly more charge cycles than a battery that is regularly discharged to 50%. Many installers consider keeping a healthy reserve of charge to be one of the best ways to maximize battery life. This is one of the biggest reasons why lithium batteries have become so popular for solar energy storage. Unlike lead-acid batteries, lithium batteries can comfortably supply much higher discharge currents while maintaining good efficiency. For example, a single 200 amp-hour lithium iron phosphate battery with a 200 ampere battery management system can easily handle an inverter drawing around 83 amperes. Even a 100 amp-hour lithium battery with a 100 ampere battery management system can generally supply that current without any problem. However, if your goal is to reduce stress on the battery and improve long-term performance, using two 100 amp-hour lithium batteries in parallel is often a better choice because the load is shared between both batteries. Another simple option is to use one larger 200 amp-hour lithium battery, which reduces wiring complexity while providing the same total capacity. In either case, lowering the load on each battery is usually beneficial for long-term reliability. Now let's take the same 1,000-watt inverter and see what changes when we switch to a 24-volt system. The math is simple. 1,000 watts divided by 24 volts equals approximately 41.6 amperes. Now connect two 12-volt, 200 amp-hour lead-acid batteries in series. Together, they form one 24-volt, 200 amp-hour battery bank. The recommended discharge current is still the same. 0.2 multiplied by 200 amp-hours equals 40 amperes. Since the inverter only needs about 41.6 amperes, the battery bank is operating very close to its recommended discharge rate. You might wonder, I still had to buy two batteries, so what's the benefit? The advantage comes from the higher system voltage, not the number of batteries. Doubling the voltage nearly cuts the current in half. Lower current means less cable heating, lower voltage drop, reduced power loss, and often smaller, less expensive cables. It also reduces stress on connectors, fuses, and other electrical components. Before switching to 24 volts, make sure both batteries are identical in voltage, capacity, chemistry, and ideally age. They should also be charged to the same state of charge before being connected in series. Just as important, every major component in your system, including the inverter, charge controller, battery charger, and protection devices, must be designed for 24-volt operation. So, when should you choose each wiring method? Choose series if you want a higher system voltage and lower current. Choose parallel if you want more battery capacity while keeping the same voltage. If you need both higher voltage and more capacity, then a series parallel configuration is the way to go. Finally, whether you're using lead-acid or lithium batteries, avoid undersizing your battery bank. A battery that doesn't have to work at its limit will usually run cooler, experience less stress, and last longer. I hope this video helped you understand the difference between wiring batteries in series and parallel. If it did, don't forget to like the video, subscribe to Battery Hacker, and let me know in the comments how your battery bank is wired. Thanks for watching, and I'll see you in the next one.